So here's the PreLab for our titration lab. It also might be helpful for you to take a look at the procedure, not only do the questions, and maybe even watch the video so you have a little bit of an idea of what you're doing when you come into the class. So let's go through the questions. We're going to be titrating vinegar with sodium hydroxide, so weak acid with strong base here. So our net ionic equation for neutralization of acetic acid, you're going to take acetic acid, this is the formula for it, add that to the base because we're neutralizing. You don't have to write Na because Na is a pathetic, and we're asking for net ionic. So the neutralization would form water, and then your salt, but we don't have Na here, so we'll just write the acetate ion because neutralization always forms water and a salt. So the next one says write a balanced equation for the ionization of vinegar. Remember, ionization and hydrolysis are the same thing. Okay, so for this one, we take our weak acid, and you can write water here or not. If you write water, then instead of H plus here, you'll have H3O plus. Doesn't matter. And our equilibrium expression is going to be Ka because this is acetic acid. Whoops. Okay, so it's important to know to remember the difference between these equations. This is neutralization. And this is ionization or hydrolysis. Okay, they're two different equations. So for procedure A, if you look through the procedure, we're going to use about 2 grams of vinegar, 1.5 to 2 grams, which is an acetic acid solution. Vinegar is usually claimed to be 5% vinegar, acetic acid. So that's what we're going to be testing here in our first part. So what's helpful, and this is helpful for all titrations, is to know about where your equivalence point is going to be. So it will help you if you know about how much sodium hydroxide you're going to need to add to your burette and put into the thing. You are going to go drop by drop at the end of your titration. So it's helpful to know, like, okay, if I need 25 mils, I'm just going to let 23 go in there and not start doing the drop by drop part until I get to the end. Because if you go past your equivalence point, you have to start over. And no one likes that. That's why people do not like titrations. Because it's very detailed, it's very specific what you're going to be doing. So what we're going to do is kind of figure out about how many mils of acetic acid of sodium hydroxide we'll need. So the first one is how much is the mass of acetic acid in 2.0 grams of a 5% solution. So we'll take our 5% and multiply it by our 2 grams. And so we get 0.1 gram of acetic acid. So in your 2 grams of vinegar that you're going to mass out, 0.1 of those is actually acetic acid, or about 0.1. That's what we're going to be testing. So the moles of acetic acid that's the molar mass of acetic acid, is this. And then you know that the moles of acid is going to be equal to the moles of base. So we can do moles of acid. Since we already have that, I'm not going to do MV because we already have just the moles, so it's easier. And then we'll do the molarity of the base to the volume of the base. Okay, here they're asking you to use 0.123 for the molarity just to get an idea. And then the volume is what you're going to look for here. And when you do that out, you get which is, oh, sorry, wrong one, which is 14 mils. So when you're doing this titration, if you know it's going to be 14 mils, you go to like 11 or 12 pretty quickly, and then you do drop by drop towards the end. I'm probably going to advise you to do about 10 because our molarity of our NaOH is a little bit higher than this one. So we're going to go to about 10, just add 10 pretty quickly, and then do drop by drop for the rest. So if we find the molarity of the vinegar, so because it's 1 gram per milliliter, our 2 grams of vinegar that we're measuring is equal to 2 mils of vinegar. So we take our moles over our liters. And so our molarity of vinegar is going to end up being around there. And we're going to calculate what it actually is. So for number 3, the graph below, which is down here, is a representation of a weak acid and a strong acid. Oh, and both of them are titrated with weak base. So mark the equivalence point and indicate the pH for each of the 2 curves at the equivalence point. So the equivalence point is about halfway through that vertical part. So for this, the strong solid line, it would be about here. And for the dashed line, about here. Okay, so the pH for the solid line is about 7. The pH for the dashed line is about 9. Which one is weak and which one is strong? The dashed line is going to be the weak acid because 9 is higher than 7, right? And we know that if we have a weak acid at the equivalence point, it's a basic solution because of that conjugate base. For the strong one, it's going to be 7. So we would say solid line is 7, dashed line is, solid line is strong, dashed line is weak, and then you can write a little explanation for that. Please make sure when you're saying that the weak acid is the dashed line, you do not just say because the strong base wins. Talk about the conjugate base because that's the real science behind what's actually happening. So for C, how is the pKa of an indicator helpful when choosing an indicator? We did talk about this in one of our videos. The pKa tells us the approximate pH at which the indicator changes color. Explain why the indicators would be acceptable for one of the titrations. So all of these 3 indicators is what they're talking about. It would be it would be fine to use any of these for the strong one because there's a long equivalence point. Okay, so there's a large pH change there. So you can really figure out based on this many mils, any of these indicators would show you. But for the weak one, for the weak acid, you would use phenolphthalein because you want to make sure you have an indicator that will change color at the equivalence point. You can see the weak acid equivalence point is right in the middle of that phenolphthalein. D, what is the value of Ka for the weak acid on the graph below? Show the easiest way to estimate the Ka from this graph. Okay. At halfway to the equivalence point, so we're looking at the weak acid. That's the dashed line. So halfway to the equivalence point, the pH equals the pKa. So that looks to be about 5. Okay. So, and you can write this halfway to equivalence point, pH equals pKa, which on this graph is 5. That means the Ka is about 1 times 10 to the negative 5. And that's it for the pre-lab. I am now going to show you how to set up the data table, okay, just for part A, because we're going to do part B together in class. So I'll just be showing you how to set up the data table for part A. But I would read through this stuff and then maybe also take a look at the video. I will say I used a faulty burette in the video, so you see that I go way past the equivalence point really fast, but you will get the idea, and we'll go over in class how to actually do it. So for your data table, again, we're just doing part A for this one. Part B, we're going to need to make a procedure in class, so I think we'll do that one in class rather than spoiling the procedure with the data table ahead of time. The first 3 here are going to be manually entered. Okay, so in class, you're going to write the mass of the vinegar here, the initial volume of the NaOH, and the final volume of the NaOH. So you'll type those in when you're doing the lab. The volume of the NaOH used, you can do minus those 2 values. That's going to be in milliliters because our burettes measure in milliliters. And to find molarity and do some of the other calculations, we're going to want it in liters. So if you want, you can just put it in there. But I think it's easier if I just make another cell for it. And I do divide this number right here by 1,000. The moles of NaOH. The molarity of the NaOH that we're going to use is 0.15. So we're going to want to multiply that molarity by the liters. So we multiply 0.15 by the liters of NaOH used. The moles of acetic acid are going to be the same as the moles of NaOH. The mass of the acetic acid is going to be the multiplication of the moles times the molar mass, which is going to be 60.1. So for the percent by mass of the acetic acid, what we're going to do is take the mass of the acetic acid, which we just found, divide it by the mass of vinegar, because that's the mass of the total solution, and multiply it by 100. Now we're going to get an error here because we don't have a number in the mass of vinegar. So we'll just type in the formula, and then when we add these numbers in during the lab, it will work out. So to do that, you're going to multiply and then divide. So we're going to divide this number and this number, and then multiply that by 100 so that we get percent. The liters of vinegar Remember that the density of vinegar is just 1 gram per milliliter, so we can take the mass, that's going to be the grams, is going to be the milliliters. So what we're going to do to find the liters is divide that number and 1,000. And then for the molarity, you take the moles and divide that by the liters. So the moles of acetic acid divided by the liters of vinegar. And if you want to just put in some numbers here to make sure you did it correctly, I'm just making these up. And you can see that these kind of make sense. Okay? So that's it for the data table for the pre-lab part.